Hello everyone and welcome to this ultimate super fast crash course on Database Management Systems or DBMS. Whether you're preparing for an exam, an interview, or you simply want to strengthen your understanding of computer science fundamentals, this session will walk you through everything you need to know. From what databases really are to how they are designed, managed, and optimized in the real world. We'll start from the absolute basics and move step by step into architecture, normalization, SQL commands, and even modern database systems like NoSQL and distributed databases. By the end of this video, you'll have a crystal clear understanding of how data is stored, retrieved, and maintained. And more importantly, why databases are at the heart of every modern application you use, from social media platforms to banking systems. So make sure you watch till the end because each section builds on the previous one, and missing a single concept might break the bigger picture. And if you find these kinds of crash courses useful, don't forget to like the video, share it with your classmates or team, and subscribe to the channel. It really helps us creating more high-quality lessons for you. Alright, let's get started. Let's begin with the most basic question. What exactly is a database? A database is a structured collection of related data that can be easily accessed, managed, and updated. You interact with databases every single day, whether you're checking your contact list on your phone, ordering food online, or scrolling through a social media feed. In all these cases, behind the scenes, there's a database storing users, posts, orders, and interactions. Now, to manage all that data, we use a database management system, or DBMS. It's specialized software that allows users and applications to store, retrieve, and manipulate data efficiently while ensuring accuracy and security. Think of it as a smart middle layer between you and the raw data. Without it, handling large volumes of information would be extremely inefficient and error-prone. Some of the most common DBMS examples include MySQL, PostgreSQL, Oracle Database, Microsoft SQL Server, and SQLite. Before DBMS, data was stored using file systems, just plain text or CSV files scattered across directories. But that approach had serious limitations. There was data redundancy, meaning the same information was duplicated across multiple files. Updating one file didn't update the others, leading to inconsistency. There were security risks, as anyone could open or edit files, and there was no concurrency control, so multiple users accessing the same file often caused data corruption. DBMS solved all these problems by providing a centralized platform that maintains data integrity, enforces security rules, allows multi-user access, and reduces redundancy through normalization. It's what makes modern applications scalable, efficient, and reliable. Most DBMSs follow a three-level architecture that separates how data is physically stored from how it's logically represented and viewed by users. This concept is called data abstraction, and it simplifies complexity by letting users interact with data at different levels. At the lowest level, we have the internal level, also known as the physical level. It deals with how data is actually stored, the file structures, data blocks, indexes, and storage paths on the disk. Above that is the conceptual level, or the logical view. It describes what data is stored and the relationships between different data entities. This is the level where database designers define tables, keys, and relationships. Finally, at the top, we have the external level, or view level. This is what each individual user or application sees. For instance, a finance team might only see salary details, while the HR team might see employee records without sensitive financial data. This three-layer abstraction, external, conceptual, and internal, allows flexibility. If the physical storage changes, user views remain unaffected. Similarly, you can add new views or modify table structures without altering how users interact with data. This separation of concerns is what makes databases both secure and adaptable. To represent and organize data effectively, we rely on data models, frameworks that define how data is structured and related. There are four major types of data models. The first is the hierarchical model, where data is arranged in a tree-like structure. Each child record has only one parent, much like a company's organizational chart. While simple, it lacks flexibility for representing complex relationships. Next is the network model, which extends the hierarchical model by allowing each record to have multiple parent records. It represents data as a network of interconnected nodes, but still requires complex pointer-based navigation. Then comes the relational model, the most widely used model today. Here, data is stored in tables, also called relations, where each row represents a record and each column represents an attribute. The relational model is powerful because you can query and combine data easily using SQL, without worrying about physical links. Finally, we have the object-oriented model, where data is stored as objects, just like in object-oriented programming languages. Each object contains both data and behavior, making it ideal for applications where data and functions are tightly coupled. A quick way to remember their evolution is HNRO, hierarchical, network, relational, object-oriented, from oldest to most modern. Before we create a database, we need a blueprint, a way to design it visually. That's where the entity relationship, model comes in. It helps us represent entities, their attributes, and the relationships between them in a diagrammatic form. As entity is anything that exists independently and has data stored about it, like a student, course, or teacher, and each entity has attributes, which are its properties. For example, student name, roll number, or marks. And entities are connected by relationships. For example, student enrolls in course or teacher teaches course. Attributes can be of different types. Simple attributes like name or age, composite attributes like full name equals first name plus last name, derived attributes like age derived from date of birth, and multi-valued attributes like multiple phone numbers. Relationships can also be classified as one-to-one, where one entity is linked to only one of another. One-to-many, such as one teacher teaching many students. And many-to-many, such as students enrolling in multiple courses. In diagrams, we use rectangles for entities, ovals for attributes, and diamonds for relationships. It's a simple yet powerful way to map out the structure before we move into database creation. Once we've designed our diagram, we can convert it into tables using the relational model. Each entity becomes a table, each attribute becomes a column, and relationships are represented using keys. Let's understand the different types of keys that make relational databases function correctly. A primary key uniquely identifies each record in a table. For instance, student_ID can be a primary key for the student table. A candidate key is any attribute or set of attributes that could serve as a primary key. An alternate key is a candidate key that isn't chosen as the primary key. A foreign key creates a link between two tables by referencing the primary key of another table. A composite key is made up of two or more attributes used together to uniquely identify a record. And a superkey is any combination of attributes that can uniquely identify a record, even if it contains extra fields. Along with keys, we also have integrity constraints that ensure data accuracy. Domain constraints specify valid data types or range for a column. Entity integrity ensures that a primary key cannot be null. Referential integrity ensures that foreign keys refer to existing records. And key constraints prevent duplicate primary keys. Together, keys and constraints maintain uniqueness, validity, and consistency, the backbone of any reliable database. Now imagine you have a huge table that stores students, their courses, and instructor details all in one place. You'd have to update hundreds of rows if one instructor changes their name. That's inefficient and error-prone. To fix this, we use normalization, the process of organizing data to reduce redundancy and improve integrity. There are several levels, called normal forms. First normal form, 1NF, removes repeating groups, ensuring each cell holds atomic values. Second normal form, 2NF, eliminates partial dependency, meaning all non-key attributes must depend on the entire primary key, not just a part of it. Third normal form, 3NF, removes transitive dependencies, ensuring non-key attributes don't depend on other non-key attributes. And finally, Boyce-Codd normal form, BCNF, is a stricter version of 3NF, ensuring every determinant is a candidate key. A quick memory trick: APT, atomic, partial, transitive. These are the three things 1NF, 2NF, and 3NF remove respectively. Normalization makes databases cleaner, faster, and easier to maintain. Once the database is designed, we interact with it using SQL, Structured Query Language. SQL is the standard language used to define, query, and manage relational databases. SQL commands are grouped into 5 categories. DDL, Data Definition Language, defines structure with commands like create, alter, and drop. DML, Data Manipulation Language, modifies data using insert, update, and delete. DQL, Data Query Language, retrieves data using select. DCL, Data Control Language, controls permissions through grant and revoke. And TCL, Transaction Control Language, manages transactions using commit, rollback, and savepoint. SQL also includes powerful clauses like where, group by, having, and order by, and we can combine data from multiple tables using different types of joins: inner, left, right, and full outer joins. We can analyze data using aggregate functions like count, sum, average, min, and max. To enhance performance, databases support views, indexes, and stored procedures. A view acts like a virtual table. An index speeds up searching, and a stored procedure stores reusable SQL code for automation. In real-world systems, multiple users access and modify data simultaneously. To ensure reliability, DBMS manages everything through transactions, logical units of work, such as transferring money from one bank account to another. Every transaction follows the ACID properties. Atomicity ensures that either all operations succeed or none do. Consistency maintains database validity. Isolation ensures transactions don't interfere with one another. And durability guarantees that once a transaction is committed, it remains even after failures. When multiple users access the same data, problems can occur: lost updates, dirty reads, unrepeatable reads, and phantom reads. To prevent these, DBMS uses locking mechanisms and isolation levels, like read, committed, repeatable read, and serializable, balancing consistency with performance. And in the case of failures, DBMS includes backup and recovery mechanisms that restore data using logs, checkpoints, and replicas, ensuring that even after a crash, data remains consistent and secure. Modern systems often store data across multiple servers and locations. This leads us to distributed databases, where data is spread across interconnected nodes but appear as one unified system. They offer improved reliability, faster local access, and better scalability. However, managing synchronization and maintaining consistency across nodes is complex. It's handled using techniques like the two-phase commit protocol. As data types evolved, not all information fit neatly into tables. That's why NoSQL databases emerged, optimized for unstructured or semi-structured data like JSON documents, graphs, and key value pairs. Examples include MongoDB for document storage, Cassandra for distributed column stores, and Neo4j for graph-based relationships. NoSQL systems trade some relational features for flexibility and horizontal scalability, making them ideal for big data and real-time analytics. Let's quickly recap everything we've just covered. We started with the basics: what a database is, and why DBMS is far superior to traditional file systems. We explored the three-level architecture that provides abstraction between physical storage and user views. We discussed data models, from hierarchical and network to relational and object-oriented. We designed ER diagrams and converted them into relational tables using keys and constraints. We learned how normalization reduces redundancy and maintains integrity. Then, we explored SQL commands, joins, and aggregate functions. We looked at how transactions preserve ACID properties and how concurrency control prevents conflicts. Finally, we touched on distributed databases and the rise of NoSQL systems for large-scale modern applications. Databases are everywhere, powering social media platforms, banking systems, hospitals, and e-commerce websites. Every time you make a search, post a comment, or transfer money online, a DBMS is silently working behind the scenes to make it possible. Understanding DBMS isn't just about memorizing definitions or commands. It's about understanding how information is stored, protected, and transformed into value. As you move forward in your computer science journey, mastering DBMS will give you the foundation to learn advanced topics like data warehousing, big data systems, or even AI-driven data pipelines. Because at the heart of every intelligent system, there's data, and behind that data, there's a database managing it all efficiently. Thank you for watching this complete DBMS crash course. If you found this helpful, don't forget to like, share, and subscribe for more deep dive videos on computer science, AI, and cloud computing. This is Knowledge Catch, helping you learn complex technologies visually, simply, and powerfully. See you in the next video.